Swayam Prabha. Digital India. Educated India.
So the most interesting question would be to say, why would we even want to do this decoupling of control from the data and centralize this control outside? And to understand this, we need to see how the traditional networks operated with the control and data being coupled, what were the challenges, and where this approach of decoupling helps. So let us try to look at the traditional networking devices in a much more detailed manner. Foremost, like what I'm showing you here, is the traditional networking router, where it has the two planes embedded in it. One is the data plane and the other the control plane. And the understanding of these two necessary planes or the terms is more vital in understanding their operations and what impact they have over each other and whether this coupling is necessary or not. But the takeaway here is that the control and data plane, they reside within the same physical device, be it the switches or the routers as I have shown them here. So what do we really mean by these control and data plane? So for this, if we refer to the RFC 7426 that put forth the SDN layers and architecture terminology, although there are many variants of definitions that are possible, I feel this would give us a right perspective of defining and demarcating the control and data plane. So by control plane, what we really mean is the collection of functions that are responsible for controlling one or more network devices. And when we say one or more network devices, we are referring traditionally to the switches and routers. In fact, this control plane, when we say that we want the functions that are responsible for controlling, it means that we are having this plane which would instruct the network devices, that is the switches and routers, in terms of how to do specific things or how to do a certain action like processing and forwarding of packets as an instruction to these devices. And that's what we mean by control planes. And primarily when we say this as a control plane, it is trying to set certain aspects which would then affect the way the device would process the packets and forward them along. And it would also have an impact in terms of how the device would operate. And this is where the separation of what the device would do with respect to the incoming packets, how it would process, being split as a data plane or also termed as a forwarding plane functionality. And by this, what we mean is the collection of resources across all network devices that are responsible for forwarding the traffic. That is strictly tied with respect to saying, given a packet that arrives, where should I send it? In the sense of, as a packet comes, what should I do with it? And that actions are taken that are on a per packet basis is what defines the forwarding plane or a data plane of a device. While the operational plane, although at the level of each device, is responsible for managing the overall operations of the individual network devices. That is, you want to enable specific monitoring, filtering of the packets, data, etc. that you want to set in terms of how the device would operate. I want to operate my router in OSPF, or I want to operate my router with ISIS. All of these become basically the modes of operation for a given device. And once that is set, the control plane is going to dictate how the actual routing as a functionality needs to be carried out. And then the data plane would look into this and say what is the means for it to forward a packet, given that an incoming packet with a certain signature is seen, where it would send. And you have looked in terms of how the routers work. So let us start from there and see how this data and control planes map. We can see on the figure here that we have a router with 6 ports. And what this really reflects back is basically you have 6 of the ports, which are both input as well as outputs. And they are connected through a high-speed switching fabric, and you have a router processor that is also augmenting to say the decisions that need to be taken. And each of these switching fabrics that we are showing is also termed as a line card for each of the port. Like P1, we have the port here with a line card, and P2, P3 likewise, and for P4, P5, P6, we will have these line cards. And in here, when we see the functionality of as the packets arrive on each of these line cards distinctly, first it does is to terminate the line, that is the physical bits that are being accumulated, and the green box here emphasizes on the line termination. And once you terminate, you prepare a frame, the data link layer L2 frame, that is done by the blue box, and then you see the packet, queue it up and see what rule you need to apply so that you decide which port the packet needs to go out on, or what is the action that needs to be taken on a given packet. And this is carried out through the aspect of high-speed switching fabric to move the data from one port to the other. And this constitutes exactly what we call as a forwarding plane or a data plane functionality. And remember, these operations happen for every incoming packet. And hence, like if we are talking about the gigabit lines or several hundred gigabit lines, we are talking about a time frame of every nanosecond you are processing a specific packet on these data planes. While on the top, what we are seeing is a routing processor that is involved in setting up the key aspects that are needed for the forwarding plane to operate. That is, when I want to run this router, should I be running a link state routing algorithm? Should I be running a OSPF mode or distance vector mode of routing algorithm? All of those have to be decided. And those are the aspects that play how a route will be decided for a given incoming packet, and then which port needs to be taken at the data plane. And hence, all the computation of the routing, the management of the device in terms of what routing algorithms to do, what ports that we need to be enabling, disabling, all of these basically constitute what we call as the routing and management part of a router, which we can club as a control plane. In fact, you can think of control plane as a software that dictates how the underlying hardware, the line cards and the switching fabric to operate in forwarding the packets. And note here, the timeline at which these routing processors may need to operate is on much more coarse grain, that is few milliseconds to few seconds at a time, and only when there is a state change of a link or when there is a state update from a neighbor, you would want to update your routes, recompute the routes and update. And hence, there is a distinct requirement of time scale of operation that they have and how they would work. And this is where we see this as a separation of data and control planes. So to look at this in a much more elaborate way on a data plane, data planes are actually the ones essential for routing the packets within a fabric from one port to the other. And the means to do this is what we call as a forwarding functionality. The packets you receive on one port would be forwarded out onto the other port. And in essence, they would also be doing several of the aspects with respect to the incoming traffic or data, be it the access control, be it the counters in terms of how many packets were received for a particular source or how many packets were destined to a particular source. And when the packets arrive, you would want to buffer and mark, like you see in the congestion control of ECN or in RED, where you would want to either take a decision to drop the packet, when to schedule a particular packet. And when it comes to the security features, you would want to inspect the content of the packet in either at the header level or at header and boot the data. So the deep packet inspections could be the functionalities. So these are all the different functions when we speak of what a data plane would do. So in the nutshell, they would match on specific bits, perform certain actions, and forward the packets out onto a specific port. while the control plane is trying to operate in a different fashion. So if we see any burst of packets that arrive, the data plane has to process them. So the data plane would operate on a nanosecond time scale with expectations of billions or millions of packets per second are served through each of these line cards, while the control planes are more or less event triggered, where any update from the neighboring device or updates or configurational changes on the device would trigger for certain activities on the routers or switches. And this might mean that we may have few thousands of packets per second to process at best. And the key operations in the data plane is primarily forwarding, but also includes buffering of the packets. When you have to queue the burst of packets that come, you may have to filter specific packets if access controls are being set in terms of what needs to be allowed to pass or what packet signatures are not allowed. And then when you have the data on multiple of the line cards, how do you schedule these packets, and what should be the quality of service parameters that you need to honor while trying to schedule the incoming packets, marking of the packets in terms of whether there is a congestion perceived, and any information that you would want to relay back to the end hosts. All of these become the functionalities at data plane. While at the control plane, it is on a coarse grain operation where you would want to see how you would want to do the routing. Like it could be OSPF that you would want to apply, or BGP or ISIS. Which of the routing algorithms need to be run to get the network, understand the network topology, and ensure that you are able to forward the packets towards the right destination. And this also includes, like, if you want to check the management aspects of the device in terms of the status, the behavior of the current device through SNMP, or extract the operational logs in terms of the syslogs, or facilitate the authentication, authorization, and access control aspects for a particular device. All of these can be done on the control plane. And what this also means is the data plane typically operates on the line cards on a hardware that's typically with a dedicated hardware ASICs, while the control plane is primarily a router software that is ingrained into the switch and would run on a switch CPU or a router processor. And notably, this data plane is an aspect that is unique to a particular device in isolation. But on the other end, the control plane, when we speak of routing and you have put multiple routers in a network, they have to work together. I cannot have one router running OSPF while the other running ISIS or link state in some other fashion. They all have to be coherent. And this is where, again, what it means in a network or a topology of a network, although the data plane and control plane are embedded in a single device, the data plane is primarily distinct for operations in terms of each device, but some aspects, not all, but some aspects of the control plane have to be common across different network elements in a given topology, in a given domain. So let's look at what we mean by operation of a switch in a given network. And typically these switches operate in a LAN, and what they allow is for multiple hosts to communicate within a given LAN. So if we look at the diagram here, if we have 5 different hosts, a switch would facilitate to forward the packets and enable communication between each of these hosts. In doing so, it would learn and remember what or where to route a particular packet given the destination MAC matches one of these MAC 1 to MAC 5. So as a very simple illustration here, a switch would basically forward upwards for any of the destination MACs that are set as MAC 1, 2, or 3, and it would send it towards down for the MAC 5 and towards left for the MAC 4. This way, the switch has a control plane which tells where to route a particular packet when you see a particular destination MAC address. And it has fundamentally a data plane which would look up this table and make a decision that, okay, I got a packet with a matching destination MAC address of MAC 1, then I would send it upwards. And this is how basically the MACs operate. But note that the MAC address is somewhat vendor defined, although you could change them, not that it is fixed and you cannot change, but they don't specify anything about the location. But within a LAN, a switch would make this location as a part of which port of the switch that it is connected to, and accordingly maintain this information to forward the packets. So at the data plane, it is MAC address to the port address mapping is what is more relevant. Likewise, when we look at the routers, which are layer 3 devices, we have seen this in earlier lectures as well, they match on the IP prefix, that is the destination IP address. And once they look up the parts of destination IP addresses, you can aggregate specific bits of IP addresses and say which way to route. And here, the routing table would say that LAN 1 corresponds to anything with the IP address 1.2.3.0, any with 1.2.3 being fixed, while any of the addresses from 0 to 255 on the last bit would be allowed to be routed towards LAN 1. And likewise for 5, 6, 7, 8 towards the right, where you would see that any address with 5.6.7 would be made, a decision at a router would be made to send them towards the right. And here you can see that the prefixes are in a way nested, and routers identify where to forward the packets based on these longest prefix match, which we have already covered in the earlier parts of the course. So in terms of when we look at the router, the forwarding table dictates the data plane functionality, and the means to populate that forwarding table is being dictated by the control plane functionality of what router 1, 2, 3 are together building a routing algorithm. Based on what routing algorithm they are trying to use would eventually dictate what forwarding table would be set up for each of these routers. So in a nutshell, when we look at the data plane and the control plane elements, think of forwarding as a means or a main function of a data plane, which tells where to direct a given data packet, which outgoing link to choose, be it a switch or a router, while one does it on a L2 destination MAC, while the other does on a L3 IP address. Whereas the control plane is primarily about routing, that is how to compute these paths so that the forwarding plane can decide where to send the packet. And in doing so, the routers do talk amongst themselves and enable to create the route, while the switches learn based on the packets that they receive and understand. Although they may not coordinate with each other, they would still be able to learn based on the traffic that is moving in and out. Hence, the data plane and control plane are clearly the distinct entities. And when we look at these operations in the data plane, that is basically forwarding the packet from one end to the other, we have seen the layering principle that puts forward a nice set of abstractions, wherein we said at the end host it will operate all the way from layer 1 to layer 7, while the switches operate on layer 1 and layer 2, the routers operate on layer 1, layer 2 and layer 3 and so on. And this enabled us to build the right set of abstractions where applications could be built on a reliable or unreliable transport, providing rolling on top of the IP, which is a best effort global packet delivery, and so on. So the abstractions were neatly defined for the data plane, which confined the roles of the networking elements to either layer 2 or layer 3 operation. But then when we speak about the control plane operation, that is doing the routing, now do we see any such abstractions in here? That is the main question. How would, if any, be needed to do the control plane operations? So first is, do we need the abstractions? Second, if we need, what are they and how should they be brought out? Let us try to look at it in detail in the next lecture.